Thank you, Professor Komang and Professor Junji. I would like to invite the third moderator, Dr. Bambang Fajar Suryadi, SSI, MSI. Dr. Bambang Fajar Suryadi, SSI, MSI is a teaching staff from Department of Biology, Faculty of Mathematics and Natural Sciences, University of Mataram, West Nusa Tenggara, Indonesia. He holds a doctoral education in Department of Biology, Faculty of Mathematics and Natural Sciences, Brawijaya University, Malang, East Java, Indonesia, and Master of Department of Biotechnology, IPB University Bogor, West Java, Indonesia. His fields of expertise and research interests includes environmental microbiology, microbiological control agent.
Assalamualaikum warahmatullahi wabarakatuh, and good morning, almost noon. I will invite Professor Muhammad Basyaruddin Abdul Rahman. Welcome, Prof. Please be seated. And Professor Rahman will give presentation on encapsulation and nano delivery of active molecule via sustainable reticular material. But before addressing his presentation, I will read Prof. Abdul Rahman curriculum vitae. Professor Muhammad Basyaruddin Abdul Rahman is currently the Senior Professor of Chemistry at Universiti Putra Malaysia and was appointed as Distinguished Visiting Scholar at University of California, Berkeley. He received his PhD in Catalysis Chemistry in 1999 at the University of Southampton. He developed skills in catalyzed at synchrotron radiation in Dewsbury, UK, and Grenoble, France. And then protein engineering at Osaka University and postdoctoral in structural biology and the University of Edinburgh. His research area include biocatalysis, chemical biology, computational chemistry, and nanobiotechnology. He is among the pioneer chemists to synergize the experimental result with theoretical insight. He has published more than 200 cited papers and 300 proceedings in wide field of biocatalysis and computational chemistry. To date, more than 20 patent applications have been filed in Malaysia and 10 patents internationally. Prof, now you have 20 minutes for presentation and followed by 5 minutes for discussion. Please, the time is yours.
Terima kasih Dr. Bambang. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera, selamat siang. Good afternoon to everybody as well. So thank you again for bringing me back to this Icon Smart 2022. I was with the first one in year 2020. And I have a big challenge today to make sure everybody sleep or everybody wake up with me. Yeah, it's almost lunchtime, right? Okay, next slide, please. I'd just like to give an overview about UPM, Universiti Putra Malaysia, or better known previously as the Agriculture University in Malaysia. We started way back in 1931 as the School of Agriculture, College, University, but then rebranding into Universiti Putra Malaysia. Okay, next. Right, I think this is a very challenging because I need to, initially I was asked to do the invited lecture, but when they swapped to the plenary, so I do have to give some insight about what I would like to talk about. Yeah, previously I worked a lot with the layered double hydroxide, the LDH, but this is more what we call as the 2D materials. Now with this, I cannot see my slide, but with this, the materials for the 21st century, it's okay. Yeah, at least I can stand up and look at that. Yeah, so hope the camera can still capture. All right. Okay, because you know, when we talk about the operation and then the most important, the application, we somehow need to change into the 3D. And today I would like to talk more on the 3D materials. For example, this one, what we call as metal organic frameworks. And this belong under this one particular category. We call it reticular chemistry. And this is very new, about 20 years old. About, you know, even some chemists still do not know what is reticular chemistry. Next slide. Yeah, so this is actually some of my works before. We work a lot on the immobilization of enzyme, particularly for biocatalysis. Next. We work with the commercial, natural, and synthetic materials. So that's why I would like to highlight the last one. Next. So reticular chemistry is looking at the materials in such a very different way. It have a very wide, what we call as a diversity. We talk about the geometry, the topology, and the complexity of the system. And in such a basic word, reticular chemistry is what we look at when the molecule is built up, or the building blocks held together by strong bonds. And this is unique about it. It requires a very simple synthesis. It's like kind of a mixture, but of course you need like kind of an oven for a certain temperature, and the condition have to be into much control, and it gives you a very unique and tunable properties. And I'm with Professor Omar Yagi. His H index is almost about maybe 180 with about 140, 150,000 citation. So he's one of the most talked about future Nobel laureate. He's basically a Palestinian, yeah? So he moved to United States. And through this, we have what we call as the Global Science Nodes, or under Berkeley Global Science Institute, under his direction. There are many different nodes or institute around the world. And we are so glad that in Malaysia, they choose us in UPM. And this is called Foundry of Reticular Materials for Sustainability. So that's why my talk a bit on the sustainability, or in short, call it forms. It's okay. Yeah, so this is actually the basic. The combination of the metal ions and in organic linkers is only limited by your imagination. Yeah, you can use any metal ions, you can use any organic acids, but of course there are certain criteria, and based on that we can make up like kind of a box, like a cage. We can also, you know, if you want to visualize, it may also look like kind of a pigeonhole. Anything that you want to do, you just do it. Yeah, it have a very tunable porosity and also very high surface area. One of the highest recorded is about 20,000 meters square per gram. So if you can imagine, for 1 gram of powder, yeah, the surface area is about what you call this a football field. Yeah, so how big it is that it can absorb a lot of, for example, gas molecules. And it is also chemically and thermally stable. So under this category, yeah, reticular materials, it also have different what you call this subcategory. For example, the metal organic frameworks, I think you can read as well. Then we have the zeolitic imidazolite framework. Is very much look like a zeolite. So it is more like kind of a cage. And the recent one, they also been working with the covalent organic frameworks. And the 2D or 3D molecule, a 2D or 3D structure is actually built up using what you call these light elements. Yeah, for example, you just can use nitrogen, just carbon, and it gives a very unique properties as well. So in terms of the application, now MOFs have been utilized in many different type of application, be it in the sensing, especially right now, absorption, for the gas storage, and many application. And you can also see that we can also tune it or make it either into nano size up to the, of course, the macro size, but we change it on the other side, macro to nano application. And next. And in my work today, I focus more on the nano delivery. Either it's a biomolecules and drug or vaccine. Most of my work right now is on drug and biomolecules. And now for the past 3 years, we venture into pesticides. Okay. So prior to why I choose more on the, what you call the, something that not many people work in Malaysia, or even worldwide, is actually on the aerosol. Yeah, we focus more on the pulmonary nano delivery because we know that there are many diseases that are related to lung is actually originated from the nanomaterials, for example. Yeah, and of course in the aerosol we're talking about the PM 2.5 hazards. There are climate change is all related, but our work focus more on the smoking related diseases, and of course lung cancer is actually still the highest. It may be the second in terms of the cancer number, but it's actually the highest when we talk about the fatality. Yeah, because of normally being detected at the stage 3 or stage 4, and normally the patient only have 3 to 6 months. That's all. So most of the technique, chemotherapy, in very invasive, you have to basically the operation. So we try to reduce it, and luckily, yeah, on the other side, COVID-19 again opened up more opportunity to us because we work more on the lung, and now we understand how to deliver drugs or vaccine to the lungs. Next. This is some of my works that we work with the Harvard School of Public Health. So some of the work being conducted in Harvard. In short, what I would like to say, our nano formulation, the droplets, it can went to a selected target of the lung region, particularly at the alveolar and alveoli. And this is actually where the most of the cancerous cell occurs. On the other side, we also show and proven by Harvard team, yeah, that the nano size, the smaller that you get is actually more toxic to the system. We've been thinking that we want to get a nano size, it is actually good, but at the same time it gives the nano environment and also killing the healthy cell. Next. So this is, next. This is the category of the, what you call this, the size, or there are many ways of doing these hubs. Next, please. Okay, we are not working only with one particular drugs, but we work with many different type of drugs. Some of the drug is actually according to the Malaysian standard, and of course also being used worldwide. We also use for, next please. We also work with the oil in water, water in oil, single drugs, dual drugs, and different system like niosome, iron oxide, where we also link with the CT scan. Yeah, the blue one is actually on liquid, and then all the brown is actually the powder system with the siRNA, graphene, MSN, and last one that I would like to talk most is actually the MOF. Next. So there are many. I have to make it very in a simplified version. Yeah. So this is actually how we look at it in terms of the schematic scheme. First, what we need to do is we have to mix up the zinc and the 2-methyl-imidazolate, and after that we add up, we encapsulate the gemcitabine. Yeah, and after that, once we get the a stable system, we then conjugate on the surface with the RGD. Yeah, this is actually a homing peptide. It is like kind of a GPS, because without it, it can go to any type of cell. Even that's why that's why the cancer patient after the chemotherapeutic what you call this treatment, they will get a lot of the side effects. But with the RGD, it will only go to the cancerous or the tumor environment. Okay, so what happened after that? When the achieve the signal, it will enter into the tumorous endothelium. Then this is when the process, the cellular uptake, and in the tumor environment, normally the pH is about 5.5 to 6, a little bit acidic, and this is when the ZIF8, in this work we use a ZIF8, start to break up and then release the drug, and that leads to the cytotoxicity, cell death, and of course lead to the apoptosis. Next. Okay, this is a bit zoom into what actually is going on into the system. If you can look at the untreated, basically just NZIF8, and then we put the gemcitabine, and of course another one RGD, the ABC. I'm not sure whether you can see that in close up, but what we can see is by adding the RGD, the cell, the system is slightly bigger. And other than that, it is very important to look at NZIF is very smooth. Yeah, even with the gemcitabine, nothing being conjugated outside. But once you conjugated it, it gives slightly rough, rough surface. And it is actually very important that I will share with you in the next slide. Next. Okay, this is actually what we look at the PX-STAR-D. We can show you that it's good thing when the gemcitabine being inside into the system and RGD, we can show that the ZIF, the reticular material retain its crystallinity. That is very important. If you lose the crystallinity, then it will not be able to deliver, and the shape also lost. Yeah. Then we can also look at to confirm the conjugation of the RGD on the surface. So we're using the FDIR on the A and the figure B for FDIR. We start to zoom and to make sure that the conjugation involved, because RGD is actually an amino acid, yeah, 3 peptides. So it have all these side change and then how it interact with the organic linkers of ZIF8. Okay, next. So again, everything is very superficial in the beginning. Yeah, physical characterization. We start to look at into the cell, what's going inside. If you look at this, we replace our drug with the fluorescent, the Fi. So the untreated, you can see there are many blue things. Yeah? Blue because we stain it with the Hoist 3342. And then on the B, you can see some green things. We can already see that Fi with the ZIF, you know, can be on the surface of the system or surface of the cell. But on the C, we can see that with the RGD, we can have more green color, meaning that can be detected in most of the cell. So higher fluorescent intensity was prominently found basically after 2-hour treatment. If you look at the table, we also confirm with the surface area and the porosity through the BET surface analysis. You know, the surface area basically reduced when you start to add up the drugs, and also further reduced when you add up the RGD on the surface, and it also can be seen with the reduction of the pore volume. So this is the most important when we look at the IC50. We run for both the healthy cell and also the lung cancer cell A5.9. If you can look at the IC50 down there, the pristine gemcitabine, basically what we like to see is that the IC50 for the system is only about 11, which is actually low, but for the MRC5 is about 27, meaning that at the end it will give you a selectivity index. In the rest of the system, it do not have that much selectivity, meaning that the gemcitabine went to the lung cancer cell and at the same time also attacked the healthy cell. Yeah, but with this one, it just mainly go to the cancer cell rather than to the healthy cell. So that's why the selectivity index is about 3.98. It's actually one of the highest. That paper was published in Dalton Transaction, and then we further investigate the dissolution study. This is our recent paper in the ACS Biomaterial, still in press, but it's already available online. The same system we study in detail using a zebrafish at pH 7.4 and cannot remember, 6.6 or 6.5 or 6.0. 6.0. And then look at the permeability. Yeah, next. So based on that, we can also link to what we have seen before. Yeah, we can say that it is the system showed the pH responsive behavior for sustaining the chemotherapeutic dissolution. So meaning that is almost like kind of a control release in especially 24 to 48 hours. One of the big issue is once you give the patient the drug, it is actually being released very fast in between 12 to 24 hours, but then it goes somewhere else. Okay, we can see from the zebrafish, it is actually the highest permeability, and then again we reconfirm that it gives a minimal adverse effect to the healthy cell, and it can be shown into the zebrafish system. Okay. But then remember I mentioned in the beginning when we do the TEM, we can see that the surface is slightly rough, but how can we confirm the roughness? So we run the AFM, the atomic force microscopy, and we confirm now that the system, the RGD ZIF system, it can be seen, the roughness is about 0.177. So meaning that the roughness of the material also assists in the penetration into the membrane. And it also have been reported in many publications before. Yeah, okay. So to wrap next. So this paper, in fact, become the cover page for the Dalton transaction, and the beauty is, you know, as a chemist, we always want to publish in Dalton transaction, and it's not beyond imagination when it being captured as the cover page for the 50,000 anniversary issue, and at the same time is the celebration of UPM 50,000. I was hoping UPM give me 50,000, but no, I don't get anything yet, but we'll try. Next. Other than MOF ZIF 78, we're also working with different MOFs, 74, 1201. MOF 1201 is actually unique because it's used calcium and lactate acid. So basically it's like kind of milk. You just drink milk MOF, what we call it, ZIF 890. And now we also synthesize our own MOF. This is the challenge that the University Berkeley put on us. So we have two. Next. So I like to change from nanomedicine, to check my time, nanomedicine into agriculture, because this is very important, especially in Malaysia, Thailand, especially Indonesia, the highest producer of palm oil. So we know the issue with the Ganoderma boninense. Next. So I'm not going to show you the detail, but you can see that per cycle, at least about 15,000 ringgit Malaysia. The price is increasing, but you have to do 3 to 4 times. Next. And what happened is when you use the hexaconazole, the normal pesticide, it increased the soil acidity, but then what happened is 90% of it being leached, become a leachate to the soil and to the ocean. So it's very bad. Yeah. So the next slide. So what we did, earlier I mentioned that it's easy synthesis, but it's not easy. So in order for us to get the first MOF, basically my student have to run at least 300 reactions for each MOF, because you have to adjust the concentration, the ratio, the temperature, and so on. So it is actually not easy, but once you get it, then you can start to work on something else. So we have the first one with the new topology. Okay, and then the second UPM MOF2, we are using malic acid and tartaric acid, but we're still using calcium as the metal ion. Next. So we also did what you call this very similar, but in this case we use a microwave technique to encapsulate it, and at the end we can release it, and what we can claim that very sustainable. The calcium later on can be uptake by the plant and reduce the soil toxicity, and also the plant acid can again further reduce the soil acidity by chelating it with the aluminium. And the best thing, it will make it easier for the phosphorus to be uptake, to be taken by the plant. Next. So it's a quick one. If you can see from there, control without UPM MOF, the Ganoderma boninens, Dr. Bambang may be familiar because it's microbiology, you can see that it's actually affected throughout the Petri dish. But with the UPM morph, the hexamorph that we use, it remain the same size even until day 180. Next. So we further study the different concentration. It is another important because we managed to reduce from 5% that currently being used in industry or in the estate to less than that. Even we can prove is 1 ppm. But of course, this is a bioassay. Next. So we start to do in the nursery trials. You can see only my hand. So we also do 2 different treatment, powder and liquid, and then we put the Ganoderma. Next. So this is very important. Last week, we've been observing it every daily basis. I normally observe every month with my student. So we can see in the control, you can see there is a growth of the Ganoderma, and even with the liquid morph, you can see also in the red Ganoderma, but with the hexamorph, even after 4 months, 5 months right now, there is no growth. Meaning that if it grows in the 6 months, we can still reduce, meaning the application may be at least 1 or twice a year, compared to the current one, at least 3 times or 4 times a year. And of course, the reduction of the, we calculated that. Next. So, I don't know about Indonesia, but I think it's moving towards that way. I discussed with my partner in Thailand. We are doing a very fundamental work, but we are being asked to do product and to commercialize this. So this is one of that. We just moving to the commercialization. I'm not sure I'm going to sell it, but there's a team. So this is some of the claim, and you can see the next slide. So this system, next, require less hexaconazole, and then we can retain it up to 21 days. Yeah, and then of course it also can act as a micronutrient. Basically, at the same time, it can act as a fertilizer. Next slide. I'm going to be very quick. So we have more right now, but at least 12. I think my student mentioned that there is another 3 new morph, different type of application. Yeah, from agriculture, pharmaceutical, electro, and solar application. Next. Yeah, this one is the lanthanide base, is glow in the dark. So we've been thinking about doing something related to the forensic. Next. Okay, this is the work computationally, but I'm not going to go detail. I'm losing my time. Inside of enzyme. Next. But you can read the paper, but what we like to say is we also not just doing the experimental work, we also did the computational work. And this is another work on enzyme, what we look at just not on the biocatalysis, but how to store biomolecules, particularly enzyme. Next slide. Normally, we can go up to 100 to 200 milligram per ml, but now we can go as high as 800 milligram per ml, to encapsulate the enzyme. Next. So this is what we think in the future, new adventure with protein and pesticide. We can do so many things with the morph, the SDG. We are looking into the reticular nanoscience, and of course, again, as a catalyst guy, so we are looking at the artificial or bio-inspired materials. Next, of course, I have to thank everybody, to thank my collaborator, thank my students, all the PhD work, and of course, without Prof. Dr. Benny, I'm not here. Thank you, Icon Smart 2022. And of course, again, thank you, Prof. Dr. Hadi, for the MIPAnet collaboration. A quick one next. Okay, this is my group. Yeah, dominated by ladies, I think everywhere. Our group dominated by ladies. But I would like also to welcome you. We are hoping to do a monsoon school. There are too many summer schools. I changed to monsoon school. So please come during the rain. Yeah, so morph work will involve theoretical, synthesis, absorption, and computational. Maybe 4 or 5 days. We try to bring Professor Omar Yagi as well, so as a guest speaker. All right, last one. But this one, just postgraduate opportunities to everybody here or online. We offer the PhD, MSc by research. All the chemistry field is actually related to me, but of course we have other field. We also like to buy coursework. It's only about 2 semesters, MSc Analytical Chemistry, and the program is being accredited by the Royal Society of Chemistry. So I think that is only one breath. So I'm giving back to Dr. Bambang. Thank you very much for your patience.
Thank you, Professor Rahman. Now it is time for discussion, and all audience, you may ask any question or share your thought about Professor Rahman presentation. Please. Any question or thought, maybe? Yes. Please mention your name and your institution, please.
Hi, thank you for the opportunity. I'm Dino Rahardian. I'm Dean of Faculty of Agriculture from Catholic University of De La Salle, from Manado. Okay. My question is, my interests are in reticular chemistry. I mean, you were talking a lot about reticular chemistry,
Right.
but your applications were into nano delivery. Is that right?
Correct.
Yeah. My question is that, have you ever tried to look at or study in using the reticular chemistry for an approach towards like, say, starch matrices or combination of nanocellulose and starch matrices?
All right.
Thank you. Thank you very much.
Thank you very much. Yeah, sometimes we have to twist our research where the money are. Okay, because nanomedicine, I think 5 years ago, there's a big chunk of money when we talk about nanomedicine. But I've been doing that for quite some time, so that's why we work on that. And agriculture, because of our university, working more on the agriculture. And at the same time as well, when we work on the MOF, we are looking at the very fundamental, yeah? And there are, under the BGSI, there are stronger group who's working in water or maybe on sensor and so on, but not many groups working on particular like what I did, yeah? To answer also, that is the first question why I did that. On the second question, right now people start to use MOF hybrid with different type of materials, especially graphene. I'm not sure about the nanocellulose, but they also already work with the polymer, what else, the ionic liquids. So I do believe that maybe some people already start to work on nanocellulose. I'm not sure about starch, because starch is actually a bit unique to the Southeast Asia. So it's actually a good opportunity to work on that. I think that will be my suggestion, yeah. Thank you.
That's a potential research to do, sir. Any question? Okay. I think it is the edge of our time for this session. And Prof, thank you for very sophisticated and very informational presentation, very informative presentation. And I will close this session. Thank you again, ladies and gentlemen. Good afternoon. Wassalamualaikum warahmatullahi wabarakatuh.
Okay, thank you very much.